Let's go on what we started yesterday. So what we set up to do was to solve a strongly coupled integrable field theory, which we obtained by just staring at the string action and saying, let's drop everything and keep only the sphere part. Okay, it's a very illegal operation. You cannot just look at the field theory and take your favorite part and drop the rest. It would be good if you could. But that's basically what we did. We just looked at the action, said, oh, fermions, I don't want to deal with all these indices. Go away. ADS is an hyperboloid, it's very non-compact. I prefer to have a sphere I can draw. So we just dropped everything, kept the sphere, and it was kind of a toy model. Of course, we don't have claims that this is a quantum truncation or whatever. It is just a toy model to understand a little bit what could be the kind of tools that we use for solving interacting integrable models. So the first thing we had to do, it was not trivial. We start with the theory, and we realized right on that the theory was strongly coupled. So even the very first starting point of understanding what are the degrees of freedom is tricky. What is a particle, and so on, what is it? We just know that it transforms into some representation of SON, which one was a bit tricky to find out. We went to large N to get some idea, and at large N we saw that basically we have N particles. So we postulate that let's assume that at finite N I also have a particle which has an index I running from 1 to N. So there are particles of N colors. Okay? There are N species of particles, and all these colors are equivalent, so there is an SON symmetry that rotates between all these indices. We saw that these particles acquire a mass which is dynamically non-perturbatively generated, that we estimated again based on large N. We saw it's exponential of minus square root of lambda times something. It's an unperturbative effect. And we see that the coupling, lambda, is not a physical observable. It's a parameter in your Lagrangian. But things, when you go and measure them, they got transmuted. Lambda disappeared, and what appears in physical quantities is the mass of the particles. So here is an example. It's the mass that enters here, and here is the S matrix, which when you write in terms of theta, is written like this. If you want to convert this to momenta, you can. You just solve, and then there will be here the arc sinh or whatever with some P over M inside. So lambda disappeared, and what replaces lambda is a mass. So this phenomenon of a coupling going into a massive parameter is what's called mass transmutation, and it's a non-perturbative effect. This is one reason why people like this sigma model so much, because this dynamical mass transmutation, it's a good laboratory for studying this dynamical mass transmutation, this non-perturbative generation of mass, which is pretty much what we expect to happen in, say, QCD, when we generate mass of glue balls. So it's kind of interesting. So these models are interesting for that reason as well. Okay, so we have particles. They are relativistic, and they transform into the vector representation. In fact, I could have started my discussion by saying, let's study a theory where particles transform into the vector representation of SON and are relativistic. Who would care about a Lagrangian? That's as good as a Lagrangian, basically. And indeed, that's a more modern point of view, where often we try to characterize. You just tell me, what's your matter content, what's the symmetry of your matter content, and then I go and try to solve the theory. If I need some help from the Lagrangian, great, but if I don't, even better. And here, you see all the information we are putting in is that the theory is relativistic, particles transform into vector representation in SON, and very importantly, of course, the theory is integrable. Integrability, in particular, almost fixes the S matrix. It leaves us a single function to fix, because all the other functions, the ratio between all other functions, are fixed by Yang-Baxter, by the requirement that if you scatter particles in different orders, you get the same thing. Right? So you see here, when you take the derivative with respect to this beta theta and put beta theta to 0, what do we get here? We get 1 here, and here we get this 2 divided by n minus 2, which gives our favorite minus 1/2 for SO6. Right? This was the R matrix, this minus 1/2 that we discussed so many times already. By the way, I tried to write this blackboard carefully because in yesterday's lecture I think I had a few typos. I put a plus here, for example, instead of a minus. So in case you are fixing yesterday's notes, I think the typos are here, here, and here. Yeah, some simple minus signs. Okay, then, so this is how far as we go with Yang-Baxter. Actually, I want to elaborate a little bit on some point that I did a bit too fast yesterday, and actually in today's tutorial you will see in more detail. At some point I said that beta was this. But you could have complained, how could I ever fix this beta just by Young-Baxter? By Young-Baxter, all we know is that there is a function of difference of θ1 minus θ2. How can you know that I cannot rescale? In other words, how could Young-Baxter know if I'm using here θ or pi times θ? Or 5 times θ? It could not. And indeed, just by Young-Baxter, you know that it's of this form with the general beta. So just with Young-Baxter, you have one function to fix plus one constant beta. This constant beta, it's just because different people can use different rapidities. For example, here we like to shift by I pi to create an antiparticle. But some people might find that that pi is annoying, so they might want to put pi times θ, and then it is just shift by I. So that depends on the choice of people. So of course, what's important is the relative normalization between what do we use for the dispersion and what do you use for the S matrix. In other words, in the language of S matrix, it's when you specify what does it mean to create a particle-antiparticle that you are specifying by how much you shift θ, and therefore you are injecting information that allows you to fix this constant beta. Okay? So this constant beta will be fixed once you say that an antiparticle is a shift of θ by θ. So this is fixed. It's related to saying that an antiparticle amounts to shifting θ by θ plus I pi. More precisely, what you will do in today's lecture is explore in more detail the consequences of scattering past the spurious state of particle-antiparticle. We did it, we sketched in the lecture what it would give, and it would give an equation for sigma, like sigma times sigma equal to something explicit. Here it is for SO6. But we took a particular set of external states, right? Red, red, blue, blue. A particular configuration, and we saw it gave something. But you could take other configurations, and all this would only be consistent if beta takes this precise value. So this is how we would fix beta. Okay? And this is what you will explore in today's tutorial. Then we get these equations. Okay? Sigma, we use this sigma shifted by up times sigma shifted down equal this rational function. And obviously, the solution is a bunch of gamma functions. Okay? Is it clear? Well, so now the goal today I want to start by filling in the gap that led to from this equation to this bunch of gamma functions with this tangent and so on. But I want to ask first, is there any question? Yes.
How do we know that the mass correction is non-perturbative?
Because we computed and saw that it was e to the minus square root lambda lambda. So it does not have an expansion at large square root of lambda. It has an essential singularity. Remember, square root of lambda is like 1 over h bar. So if you think what we got was something e to the minus 1 over h bar. So when h bar goes to 0, it's an unperturbative. It goes to 0 faster than any power. Other questions? Okay. So today, and well, this is almost the solution of the theory, because as we said, in an integrable theory, if you know the dispersion relation and the S matrix, you are almost done. Almost in a sense that, for example, you can now put the particles in a big circle and compute a spectrum of this system for particles in a big circle. If you put them at an infinite line, then this is really the full solution, because then the spectrum is continuous, you can put any momenta, and the physical question is what happens when I scatter 5 particles against 5 particles, and you know it just factorizes, and you just use this. So if you are at infinite volume, this is definitely the full solution. And even if you are at finite volume, it's almost the full solution. You just impose that as a particle goes around and scatters with everyone, you get 1. And if the particle is at small volume, then it's more tricky, but it's actually also the full solution, but this would require some explanation. Okay? Okay, good. So I want to spend some time with some simple math, because I think this is the kind of equation that you might encounter in many situations. So I want to tell you, actually not one, but a few ways of solving this equation. So the goal is just to solve this equation. Sigma of θ plus I pi over 2 times sigma of θ minus I pi over 2 equal to θ plus I pi over 2 divided by theta minus I pi over 2. Can someone do a following check? Or gang, maybe you did it yesterday. This tangent, is it a zero mode? Namely, if I put this tangent on the left-hand side, I get 1. Is it true? Tangent shifted times tangent shifted is equal to 1, right? That's right. But the tangent is periodic with period. Good. Silly. Okay. So I was just in my mind trying to okay. Very good. So, by the way, let's see that this is equivalent, of course. I'm not sure if I'm going to use it, but maybe we will solve instead this equation. F of x plus I over 2 times f of x minus I over 2 equal x plus I over 2 over x minus I over 2. It is just rescaling of theta by pi. Then we get rid of pi's in many places. Perhaps we could solve this instead. Right? It's the same. If we solve one, we know the other. I'm not sure. Yeah, let's solve the second one. Second one looks better. Okay. Is it okay? Good. So, so how do we go about solving this equation? So any proposal? Maybe you want to propose, then we can do a few more ways. If you have a proposal, we can do it also that way. Proposals for solving this equation. Take a log. Take a log is a good idea. So let's follow that idea. Let's take a log and see if we become more inspired. Log of f of x plus I over 2 plus log of f of x minus I over 2 equal log of x plus I over 2 over x minus I over 2. So why is this helpful? What could we do next? Now instead of product we have sum. That's what we gained by taking a log. And now what could we do? Any proposal? Now there are two proposals. There are two things we could do here. And now I'm going to do both, but sorry? We could differentiate. We could differentiate. And if we do, let me introduce the function g to be the function f prime over f. So it is just, in other words, the derivative with respect to f of log of f. Just not to carry too much notation around. Then we simplify. Then the equation we are trying to solve is the equation g of x plus I over 2 plus g of x minus I over 2 equal. And now we need to take derivative of this. Derivative of this is 1 over x plus I over 2 minus 1 over x minus I over 2. So we put the same denominator. There is minus I over 2. Minus I over 2 minus I over 2. So it gives minus I. So it's equal to minus I over. So I want to multiply by I to kill that stupid minus I. So I multiply by I. I multiply by I, this is my definition. And then here I get 1 over x squared plus 1/4. Right? Good, so this equation is indeed very closely, so I don't know if you find this is an improvement, so we went from this equation to this equation. It's actually an improvement, but what about the next step? How do we find a function g that obeys this equation? can take more derivatives. We can. It's not the way to go. So any proposal here? You have to solve this kind of equation. What could be the tricks that we know? What kind of tools do we know? There are not that many. Sorry?
Poles and asymptotics, maybe?
That's actually one possibility. One possibility. We could look at the poles and the asymptotics. In that case, I would say that it's actually a good idea to start here. And indeed, that's a good strategy. So that's another direction. But now we are in this direction of taking logs and derivatives. I want to, but as a third way of solving it, let's solve it as you are proposing after we finish this one. So here, let me propose one way. Let's Fourier transform this equation. Fourier transform is typically good because shifts in Fourier are very simple. They are just multiplicatively renormalized. So let's multiply the equation by e to the I kx times everything, and we integrate over k. So we integrate over x. And integrate over x. So we Fourier transform. Now, what's the Fourier transform of the right-hand side? What's the Fourier transform of a Lorentzian? A Fourier transform of a Lorentzian is the following. So we are integrating a Lorentzian, and we have a pole here at I over 2, and a pole here at minus I over 2. Right? And we integrate e to the I kx times a function that has a pole here and a pole here. Now what we do is we close the contour and pick the pole. But do we close it up or down? Well, it depends on the sign of k, right? So if k is positive, for example, we want x to have a positive imaginary part because I times I is negative. So what we get from the Fourier transform on the right-hand side is e to the minus, we put x at the pole, absolute value of k over 2. Right? What about on the left-hand side? Okay? On the left-hand side. Well, on the left-hand side, let me massage it a little bit. And let me write this as e. I add and subtract I over 2 here. So I write this as e to the minus. So I put here plus I over 2 and I subtract I over 2. So minus gives plus. So e to the k over 2 times the integral dx e to the I k x plus I over 2 times g of x plus I over 2, right? Where we integrate where over the real axis, plus a similar integral where I write e to the minus k over 2 times integral over r dx e to the I k x minus I over 2 times g of x minus I over 2. Okay, so I did nothing here. I just completed the exponential and separated the integral into 2. Okay, next step. What do you propose now? So what we have here is that we have this real axis, but we are evaluating it at x plus I over 2, right? So this is equal to e to the k over 2 times integral, not over the real axis, but over the real axis shifted by I over 2, right? E to the I k x g of x plus e to the minus k over 2 times the integral over the real axis minus I over 2 e to the I k x g of x. Right? And now why don't we just shift the contour from minus I over 2 to 0 and from plus I over 2 to 0. Okay, so far we have been utterly mathematically rigorous, but now let's put here an equal sign, but let's put a dangerous sign. because now we are going to do something a bit dangerous now, which is we just shift the contour. We are integrating. This is the real axis. And we are integrating here, and we are integrating here, and we just shift the contour of integration. We can do integrate. We know, of course, that the contour doesn't matter. I can put some small bump and so on. So why not just shift it, both of them to the real axis? Right? And if I do, then I get these two exponentials, e to the k over 2 plus e to the minus k over 2 times the Fourier transform of my function of k. And in this way, I conclude that the Fourier transform of my function k is equal to e to the minus absolute value of k over 2 divided by 2 cos of k over 2. And now we will solve the problem. Now we inverse Fourier transform, compute the Fourier transform. Then we get g. G is the derivative. We integrate once, we get log f. We exponentiate, we get f. Okay, now we are done. I mean, computing f or computing the Fourier transform is the same thing. Now it's just a question of going to mathematics and computing the Fourier transform of this object back. Okay? Any question here? So then you ask me, is it true that if I take this g and I compute the Fourier transform of this object, okay, then I get g is the derivative of log f, or said differently, if I take that sigma over there with all these gamma functions and so on, take the log, then take the derivative, is the object that I get the Fourier transform of that? And the answer is almost, but it's not. Yeah? So let me tell you what this is. This part here, this result here, if I just take the Fourier transform, what I would get is almost the full result, but I would miss this tangent. This is this. Okay? Let's postpone a little bit. Let's then make a comment of how could it be, because we solved this equation. Okay? And the point is that this tangent is a zero mode of this equation. Namely, if you take this tangent is a function that if you shift by pi over 2, flips to 1 over tangent, because cosines and sines exchange. So if you multiply tangent by the same argument shifted by theta by I pi, which means the full argument is shifted by pi over 2, you just get tangent times 1 over tangent, which is 1. So clearly, if I have a solution, I can get a new one by multiplying by any tangent. I multiply by this tangent, I can multiply by another tangent with pi over 7. And so the solutions cannot be unique, because I can always go to this equation, and if I have a solution sigma, multiply sigma by some tangent, and it's a new solution. So this is kind of a zero mode. So there ought to be one step of the way that we did here, where we could have gotten into trouble. Okay? And I will come back to this point, but it's precisely here where we have to be careful with zero modes. And we will come back and see what exactly could be going wrong. But can someone anticipate already what could be the problem? What can be the problem is that you cannot always shift contours. You can shift contours if you have no singularities on the way. If you have singularities on the way, you have to be more careful. You have to pick poles. So the last step where we said, up to here everything is perfect, totally rigorous. But then when we shift these contours and say that we just go to an integral over the real axis, which is this without this I over 2, which is what we call g hat, that was dangerous, because we assume that on shifting there are no singularities. Okay? Now let's find, so this is derivation number 1. Now let's do derivation number 2. Okay? And all these derivations, you will see, will have a subtlety. And with all of them, we will get only the first factor, which is already very good, because it's the hardest part, all these gamma functions. And then I will fix all of the derivations to get also the second factor. Yes?
Presumably, though, like this method could still give you the second factor.
Oh, yeah, absolutely. We are going to improve it. So right now, we are going to write 3 blackboards for 3 derivations. And then we are going to clean up a little bit each of them to make it absolutely perfect and get even this tangent. This tangent, it's what people call in integrable models a CDD factor. This CD and D are people. CDD factor is an ambiguity. Whenever you have this integrability method, you saw it was quite powerful. It fixed almost everything. Then it gave you a functional equation for sigma. And then you solve it, but there is a space of solutions to this equation. And the ambiguity is parameterized precisely by this kind of CDD factors, which here we see very simply. Any function that is under a shift of I pi flips to 1 over itself, I can add to my equations, and I will not spoil anything. So what we will see, how do we fix then is zero modes? Then it will be physics. And we will see that physics will tell us that we need this factor there. Okay? But at this moment, let's continue the derivation. Then we will find 3 times that we get only the red term. And then we will ask, why isn't this red term good? What is the physics of this solution as it is that is needing some fixing? And then we'll understand how to fix it. So the second way of solving it, the first part is the same. And we want to solve this problem of solving this. G of x plus I over 2 plus G of x minus I over 2 is equal to some known function of x. Suppose we want to solve this problem. Okay? For us, this f of x is a Lorentzian, but it could be any function. I'm going to tell you how could we solve this problem in general. One way is, of course, Fourier transform, as we said, and then what you get there, instead of the exponential on top of the final formula, you put a Fourier transform of this capital F. But let me show you another way of solving it, which I find very cute, and which is generalizable to other functional equations of this sort. And the idea is the following. Convolute this equation. Let's convolute this equation. What is a convolution? Means that I multiply by a function and we'll put here the argument y minus x, and we will integrate over x. So this is a convolution. And the function that I'm going to put is the function cosh of pi times this. So this is an example where I would prefer to use the original equation with I pi, then I would not have a pi there. But okay, as it is, there is a pi there, I think. Okay, we will see. So the idea is multiply by this kernel and integrate over x. Okay? You say, why do you do this? It looks a bit crazy, but okay, I want to do it. Okay? And now you'll see why it is very interesting. Let's now study the left and the right-hand side. So the right-hand side is what it is. It's something explicit. If you know this function, you compute this integral, you get something. There's nothing to say. It's just whatever. So this right-hand side is explicit. So this is a new function, f tilde of y. Okay, this is explicit, we know it. Right. You give me f, I compute this integral. Right, nothing to say. But now the right-hand side is quite interesting, because what do we have here? What do we have here? I have an integral over the real x's of this function. For each term, I can again go to the cosh and complete and add and subtract to x I over 2, which converts it into a sinh. And what I see is that the left-hand side is equal, and this step is rigorous, we did no approximation, is equal to an integral over a contour gamma of g of x over sinh of pi x minus y. Where this contour gamma is the contour where I go over the real axis here, where a distance minus I over 2, and then I go back upstairs at some height I over 2. Okay? So this is the contour gamma. It's a union of these two contours. And I'm integrating this. Okay? Now, if the function is well behaved at infinity, I can close this. This is not a problem. We just add a little bit. So here we are assuming that the function decays fast enough at infinity, and I add these small pieces at infinity. Okay? So this here is assuming that G is well behaved at infinity. It doesn't need to be very well behaved. It can be slightly bad behaved, because you see, you have an exponential suppression already at infinity. So It just doesn't, it cannot be exponential of y squared or something like this. It can be any polynomial, for example, behavior at infinity. So it can actually be quite naughty, but not super. Okay, so then we close this into this rectangle. And now let's say that y is here, is a point inside. Okay? Y is a point inside. But then I just shrink the contour. I just shrink the contour and say that I have my integration of my rectangle goes to, I just shrink the contour. And I get an integration around the point x equal y. But at x equal y, sinh is 0, so there is a pole. Right? And therefore, I just compute this by residue, and this gives g of y. So g of y is equal to this explicit function. Okay, we are done. Okay? So this is the solution. What is dangerous here? Well, what's dangerous is, well, can we really shift this contour? We can if there are no singularities inside. What if there are singularities? If there are singularities, this was illegal. So this step here is where the danger is. Let's put again a dangerous sign here. So this assumes no singularities inside the strip. Which was exactly the same assumption as above, by the way. Let's just write it there as well. Here, this shifting here, the fact that we can shift, assumes no singularities inside the strip. Okay, yes?
The intuition behind choosing the convolution with this exact function is, couldn't we choose like simpler function with similar properties?
I don't think there is any. What function would you imagine? So, yeah, I don't think there is any function that has.
Like, for example, function that would also have a pole in y, but will not have sinh in denominator.
This is the okay. So let me tell you. No, there's no such function you could shift because you need to have a function that shifted by I over 2 and by minus I over 2 gives the same function. So it's immediately a trigonometric function, and then it must be sinh. Now, what is the connection between these two approaches? Well, one is just a Fourier transform of the other. It's very similar, right? And indeed, it's a fun fact that 1 over cosh, you see, is appearing here in two positions. It's appearing 1 over cosh of k over 2 up there. And here we have 1 over cosh, almost the same. Up to some pi, it's almost the same. Right? These were the functions playing a key role. In Fourier, it is you multiply by 1 over cosh, whatever the Fourier is. And here you convolute by 1 over cosh, whatever it is. Multiplication in Fourier becomes convolution in position space. So what this is telling you, and you can check, which is an interesting fact, is that cosh is a function that is as its own Fourier transform, is equal to its own Fourier transform. Okay, up to, you can normalize such that it's exactly equal. Right now we have some pi and 2. So it's fun. There are not that many functions, but under Fourier transform, these two functions go to each other. We know also that Gaussians, for example, are another example that have this. A Gaussian goes to a Gaussian, right? But it's fun that here is another example. 1 over cosh, the Fourier transform is 1 over cosh. I don't know if there are many more functions with this property. But it's a true statement. So this function, you do not need to guess it. You could just compute the Fourier transform of 1 over cosh if you wanted to see what would be the counterpart of the derivation above, and you would find that it is 1 over cosh. Okay? Are you happy? Is it good? Okay. Finally, let's solve it in another way, which I like it, which is a bit, some people would say it's very illegal. But let's introduce this operator D, which is a shift by I over 2. Okay? It's an operator which shifts by I over 2. Okay? If you act with D on a function, so D times a function of x is of course equal to the function at x plus I over 2. Okay? Let's also use the notation that if instead of doing this I put f to the power d, what could this be? And someone proposed, this is definition now, it's not, you cannot, what could this be? F to the power d. Yeah, how could I ever make sense of such crazy thing? F to the power of shift operator. You see why I like this derivation. It's full of fun things like that. So what could this be?
Log.
Yeah, very good.
Log n.
Exactly. The way to make sense of it is to say that this could be this. Right? So this would be, this thing here would be e to the log of f of x plus I over 2. Okay? Good. But then it's kind of fun, because then with this notation we can see that that equation there, the second line, can be written in a cute way. The second line we can write as saying that we have f to the power shift operator plus inverse of shift operator, which is just you put e to the minus instead of e to the plus, is equal to x to the power d minus 1. Okay, so please absorb it a little bit such that you see that this is the second equation. See? Is it too shiny? Can you see? Or because of the reflex you cannot see? I cannot see from here, but it probably means you can see. My angle is different. So is it okay? Do you agree that this is, because this is x plus I over 2 over x minus I over 2. So this, using that definition, this funny equation is nothing but the second line. Do you agree? Yeah? So okay, so now we solve it. We want to find the function f. So f is x to the d minus 1 over d plus d minus 1. Okay. But now this looks a bit insane, because we have to make sense of this expression. So now let's make sense of this. So what could be this expression here? Well, let me write this in the following way. Let me say that this is d square over d square plus 1 minus d to the minus 2 over 1 plus d to the minus 2. Okay, this is true, just an equality. Okay? Now, there are many ways of interpreting this equation. I'm going to choose one. It's not the most natural way, actually. And you will see that, you will see what it is. And now I write this in the following way. This is just, what? This is just, I think I am doing some mistake here. Am I doing some mistake? Let me just confirm that this is the clever one to do. Okay. Okay, so this is sum from n equal 1 up to infinity, minus 1 to the n plus minus 1 to the n minus 1 d to the 2n, the first term, minus sum from n equal 1 to infinity minus 1 to the n minus 1 times d to the minus 2n. Okay? Just because I want. So f to this power thing, f to this thing, is equal, as we said, to exponential of sum from n equal 1 up to infinity, minus 1 to the n minus 1. And then we have this term, which gives logarithm of x plus 2n times I over 2, plus this term here, or minus that term here, which gives minus log of x minus 2n over I over 2. Okay? Now, this is slightly annoying because it's not very convergent. You see, when you take n very large, it doesn't behave super well at infinity. So if you want to compute this sum, what it's useful to do is first you take d dx, then you compute this sum, and then you integrate back. It is just a trick to regularize this sum. Okay? And when you do it, what do we get? We get the red thing. Yeah? We get exactly this term here. It's just a statement that log of gamma function derivative is psi function, which has a representation as an infinite series of poles. Okay? And now, what was the dangerous step here? Okay, I can put a big, a big symbol here. Everything was dangerous here, but strictly speaking was this part here. It was the fact that I can represent this as many different terms. I can split terms in many ways and generate many different infinite sums, all of which, if I would resum as if they were numbers, would give to this. There are many ways of understanding this. I can, for example, take this and expand this at small d. Here I split in two, and part I expand at small d, part I expand at large d. It was arbitrary. It's true. It's a true statement if d was a number. But I could just take this and just series expand it. I could take this and just write this as an expansion. This is also equal to what? It's also equal to 1 minus 2, or 1, I add and subtract. I subtract d, and I add d. So adding d, subtracting d is minus 1. Minus 1 plus 2d square over 1 plus d squared. It's also equal to this. And I could take this expression and series expand it at small d and get something a bit different. I could do many things. Right? So this is the dangerous step when we choose to expand terms in a particular way. But that just means that different ways of interpreting this would give different solutions. So if we want to find one, this is good. We find one solution. And then other ways of treating this formal expression would give other solutions to this equation. Okay? Okay, good. Now, let's see a little bit. Let's now try to correct this a little bit and understand better why do we get then. So this, again, would lead to the red part of the solution. So the point is that all these solutions, they are leading to this red part here. And this red part here, let's see, where does it have singularities, this red part? Just to make sure that at least it is okay. Well, it has singularities when these gamma functions up here, or let's say different. When does the log of this expression have singularities? Because we were taking the log several times. So if I want to go to see singularities of the log, I want to look at poles and zeros of this expression. Right? Because when I take the log, poles and zeros are equally bad. So I want to look, therefore, at the poles upstairs and at the poles downstairs that become zeros. Right? So I want to look at the arguments of gamma function and see when does the argument become equal to 0, minus 1, minus 2, minus 3, which is where the gamma functions have poles. Right? So you see that the points that are dangerous here, if I draw the complex plane, this is dangerous when theta is equal to 2I pi, okay, minus 2I pi, but also from this second term I pi, and here minus I pi downstairs, or actually this minus I pi is from the one upstairs, and the I pi is from the one downstairs, and there is a tower of that. Okay? And indeed, this is the singularity structure, so we were considering a strip that was here, at I pi over 2, so this was totally safe. There are indeed no singularities inside here, and thus it worked nicely that we could indeed use all this. That's why all these derivations were leading to something there. Okay? So now, suppose, however, this guy here, it has a singularity. This guy here, this tangent, it has a singularity when theta is pi over 2. Okay, so it's not really inside, but it's at the boundary. So this tangent here, if I put it here in yellow, this tangent, it does have singularities. Let's put with small balls. So it has a singularity here, here, and then shifted here, here, and so on. Okay. So this is the source of our exclamation marks there, and of the source that some things could fail. It's precisely because this tangent has some singularities at the boundary. Okay? Okay. So okay. So you might think that being at the boundary is still safe, but if you analyze a little bit the argument, you see that it's not. If you have at the boundary, what is safe to do is shift them all by I epsilon or all by minus I epsilon. That's fine. That you can do. But if you do, then one of them necessarily is inside. If you shift a bit up or a bit down. If you want to regulate a little bit, you can shift all these yellow lines by a little bit. But you cannot open them up. You can just shift them by up or shift them down in a way that one of them will be inside the strip. Okay? Okay, so now we understand that. Let's start by the last derivation. The last derivation here, why did we choose this? What is special about this way of expanding? What's special about this way of expansion is that you see that by separating it in these terms, we start putting singularities very far away. The first singularity is shifted by 2 units up. And here the first singularity is shifted by 2 units down. Right? So this is what we would get if we would want if we knew that the singularity structure was like this, starting at I pi and going up. I pi is twice pi over 2. And starting here and going down. If we knew we want these singularities, the ones drawn here, then that decomposition will be the natural one. It's the one where when I expand, I only have these with powers bigger than 2, and I only have 1 over these with power smaller than minus 2. So that explains why this gives this term on the nose. Now, if I wanted singularities inside, for example, suppose I want a singularity at 0. Right? I want a singularity at 0, a pole at 0. It's easy. If I want a pole at 0, let's use this one. Because you see, if I put this thing here, this minus 1 gives a 1 over x, and then the expansion of this starts with singularities at 2, 4, 6, and so on. So if I use this, I will get a function that has a pole at 0, and then a bunch of zeros at I pi, 2I pi, 3I pi, and so on. So this would be another solution with very different analytic properties. Okay? So, okay. The difference between them, as we know, are these CDD factors, these tangents here and so on. Okay? So, why do we like this? So, and the answer is actually very simple. What this function is doing here is putting a 0 when theta is I pi over 2. Okay? This function here serves an important physical purpose. It adds a 0 at theta equal I pi over 2. And why is this good? Because remember that zeros of the S matrix, why is this good? Because there is a pole here when theta is I pi over 2, coming from this term here. So this term here, when n is equal to 6, becomes 2, so becomes, when n is equal to 6, this becomes 4, becomes 2, this becomes I beta theta, I theta plus 4. Here this is wrong, sorry. No, that beta is wrong. There must be a 1 over pi. That 2 is probably a pi, or there is a pi missing, sorry. Yeah, this 2 is a pi. So when n is equal to 6, I get 2 over pi. When n is equal to 6, 2 over pi times 2, and here I get 4. When n is equal to 6. So this gives, sorry, 1 second. Yeah, this is good. N is equal to 6. 6 minus 2 is 4. 4 over 2 is still 2. So I get 2. 2, 2, 4. And here, n minus 2, 4. So this would give a singularity at theta equal I pi. I don't like this. So perhaps it's this one. Let's see this one. This one gives 1 plus n equals 6 gives 4. 4 over 2 is 2. So 2 I pi theta. It's from this guy actually. Okay. Good. So this guy as a pole when theta at that value there. So what this 0 is doing, it's canceling a pole of the matrix part. Okay? And here you have to put physics. You have to say that my theory should not have these poles. And how can we argue if a theory should have poles or not? Well, this is the analysis of bound states. Right? We saw that poles or zeros of S matrix, they have meaning. They are not some random thing. So now you have to ask, forget about the Lagrangian. You are describing a theory of n particles which are relativistic. Now there is a physical question. Do they attract and form bound states or not? Okay. So this is not a math question, it's a physics question. And the point is that these particles don't form bound states. Okay. We could check this, for example, by large n. We saw they were free, and we could try to compute the next corrections and see if the interaction is attractive or repulsive. And we'll see that they don't want to form bound states. Well, but if they don't want to form bound states, I need to get rid of this singularity here. Okay? I need to get rid of this singularity. And to get rid of this singularity, I need a new 0. So I already have my solution, and I need to put a new 0. So then I use this 0 mode that allows me to put a 0 for free. And I don't want to put more, because there are no other singularities to cancel. If you see, all the poles are cancelled already. And so if I would put other tangents, I would introduce necessarily other poles that would correspond to new bound states. Okay? So perhaps there is a quantum field theory without this factor, where we have a theory of particles, and these particles can form bound states. Who knows? We can postulate its existence. We just say, I don't put this factor. Now there is a pole at S matrix, so these ON particles form bound states. Why not? But then I would not know which theory we are talking about, which is fine. It is some theory of particles that can form bound states. Okay?
So this factor came from the normalization you imposed with R theta, R minus theta equals 1, no? The denominator?
Yes, that's true. That is true. So if I had not chosen this normalization, however, then what I would get here would also be different. So then we'd also have to rederive it. So this is what it is because I chose this unitary friendly normalization. Otherwise I have to change this, and then the argument why we get this is different. Okay? So this is it. So by the way, how do I get these tangents? If I really insist in doing it in this funny way, then I need to do something like doing some crazy math, like saying that I start with this. I can clearly do something like this, right? So this is just x, right? On the one hand. But then if I start manipulating this in some funny ways and expanding it, I get some tangent out of the blue. So this is telling me that this is a zero mode. So there is a proper way, or if I put here this minus 1, this is equal to 1, right? But it's equal to 1 in this new world of new math, where I put x to the 0, it's equal to 1. But now if I take these, split them around, expand in different ways, and so on, I get my version of 1, which is whatever I want, but whatever I want are these tangents. So you can find the tangent by carefully playing with how you interpret this equation. One of the ways gives this tangent. Okay? So this is how we see zero modes in this fancy language. Okay? How would we get them directly from above? It's actually quite interesting and nice to see how we could get it. So suppose we want to derive it here. But what we are saying now is quite simple. We are saying that there is a singularity here that we want to put. So we want to put a singularity here. We say there is also a singularity here. So when you shrink the contour, now you get an extra contribution. You get a contribution from integrating around this extra singularity that we are adding. Okay? And potentially one down here as well. If a function put a singularity there, you put one in the bottom. Okay, so these are these singularities here that we know we want to put, right? So we don't solve the equation, but we just say, I can predict this picture with poles just from physics. So I know I want a singularity here and then, one here and one here, right at the boundary. Sorry, right at the boundary. What I wrote is wrong. It's right at the boundary. So, okay, so right at the boundary, what happens is that I want to put the singularity right at the boundary. So when I move up or down, I can say that one of them is slightly here and the other one is slightly here. Okay? So if I would follow the derivation. So now this one is inside, and when I shrink, I also have to pick this extra contribution. Okay? But now it's actually very simple, because this is a contribution of g. But g is the log derivative. So what's the residue of a log derivative? It's 1, right? Because it's the derivative of a log. It's what we saw in lecture number 1 when we were doing harmonic oscillator. Log derivatives have residue 1, right? Because it's a log, it's clear? Log derivatives have residue 1. So this thing here, the extra term that it gives, if there is a singularity, this extra term, I just have residue 1, I just put 1 over sinh at that particular position, at pi, when x is equal to x star, at the particular position minus y. Okay? And now all I have to do is to know that when I take this expression and I do the integral over y of this gives indeed log of tangent. And this is the new term. The integral of 1 over sinh is log tangent, and this is how I would get immediately the extra term that I would add to this f tilde, and therefore getting the yellow stuff. Okay? Similarly up there in Fourier, you can also fix it in the similar way. Okay, so let's now, before concluding, summarize a little bit what were the kind of crucial ingredients that we should aim at having if we want to solve the ADS-CFT model. So what do we need? So we concluded our study of the ON. This I thought would take 10 minutes to finish this gap, but it took 1 hour. So, but okay, I think this is useful for you to know. It's an important piece of math. So let me tell you a little bit what's the summary. What do we need to study now our model, which is the ADS-CFT model, where we have some particles moving and scattering with each other, and we want to compute its S matrix and its dispersion and the dispersion relation of this particle. We want to solve this theory as well. Okay? So now this here is the ADS-CFT model. Remember, we call it ADS-CFT model. We can call it the string theory, or you can call it the spin chain. But given that a spin chain becomes very, very non-local as you increase the coupling, or given that the string becomes very, very vibrating as you decrease the coupling, we call it something in the middle to indicate whatever replaces these notions of string and spin chain that we know hold respectively at strong or weak coupling. So we have this ADS-CFT model, so what should be our wish list? What do we want out of this model? So the first thing we want to understand is what is a particle, right? So this is the kind of questions we have to prepare ourselves to answer. So what is a particle? Okay. So a particle moves with some dispersion relation, epsilon of p, or equivalently, I can perhaps introduce, like we did for relativistic, this epsilon. And the first question is, what is this epsilon? How do I fix this? Okay. Let me tell you that this is non-trivial. For example, we know something about this. We computed it at strong coupling. At strong coupling, we have a relativistic sigma model. So at strong coupling, we know that we get something like this, square root of 1 plus p squared. If I normalize properly, actually we did not see, but you can believe that, okay, it's a relativistic sigma model and so on, it should be something like this, and it is. We saw at weak coupling what it was. At weak coupling, it was, let me write at weak coupling in the following, let me say the following. So, yeah, let me write and use energy equal, sorry, at weak coupling it was 1 being the classical energy. If I put an excitation, it has classical dimension 1. And then there was some correction, which was lambda sine square of p over 2, up to some constants. There was some constant here, maybe over pi square, something like this. Okay? And the question is, so this is when the coupling is very small, and this is when the coupling is very big. In fact, if you do it carefully, there is a lambda here. Okay, up to some factors, it's what it is. And you see that what we are after is something very weird. It's something that should interpolate between something that looks like a spin chain, the top expression, and something that looks like a relativistic particle. Right? So this, what we are after is a function with, it's not a spin chain, it's not a relativistic particle, it should be something that has a flavor of both. Okay? And this is question number 1. You see, already question number 1 is much tougher than in our toy model, where it was just something like this and that's it. Now, even understanding what is a particle in this ADS-CFT system is much richer. This question. But then the particle itself can have some degree of freedom, A. Okay? So A will transform in some representation of some group. What representation and what is the symmetry group for our excitation? Right, now I have to look at all possible matter content of n equals 4, understand everything I can put on my spin chain, what's the symmetry that rotates all this stuff. Or on the string theory, I have to go to my string theory, understand what's the symmetry under which particles transform. Okay, so that's problem number 2. So there is this understanding what are these excitations, and understanding what is its dispersion relation. Now, since we are talking about this dispersion relation and this excitation, we can jump a little bit over the S matrix and go to the second thing that we can ask, that we will need later, which is, what is the spurious state? That is, what is this state that we can create of a pair of a particle and antiparticle that later we will use to scatter it past an S matrix and impose that the scattering is equal to 1? This is a question we can ask at this point. All we need to know is what is the dispersion, such that we can create a state with energy minus energy, momentum minus momentum, total singlet. So we already have everything it takes. We can already answer this question at this point. Then we need to make an ansatz. Once we have these questions, we make an ansatz for the S matrix, that will have these incoming indices AB and outgoing indices CD. And that will depend generically on U of the first particle and V of the second particle, or U1 and U2. And now there's no boost invariance, nothing. We cannot just say that it's U1 minus U2. Now it will be a more complicated function of two variables. We cannot use Lorentz invariance a priori to say anything about the dependence on U and V. The theory is not Lorentz invariant, you see here. It's a more complicated theory. So we make an ansatz, and then what do we use? We use symmetry. This just means that I cannot write random tensors, I must write something proper. And I use Young-Baxter to try to fix as much as possible given my group. Okay? Then, as a next, and finally, I use crossing, which is scattering past this virtual particle should give nothing. Finally, once I have this, we construct bit equations using the ingredients we constructed, using the dispersion, and the energy will become the sum of the energies of all these particles. And this, at least for large strings, will therefore solve this important problem of understanding the spectrum at any finite coupling, which we said was equal to the energy of strings at any finite string tension. At least for large operators. For large strings, where this circle is big. And then we have to solve this for any strings, not just large. Even if we do all this, then it is still only for big strings. Then we have to go to smaller strings and understand what to do. And then we have to understand all other physical quantities, which is a big exclamation mark, because this is just the tip of the iceberg, just the spectrum, just the two-point function of the theory. So then after all this, we have to go on and study Wilson loops, scattering amplitudes, 3-point correlation functions, 4-point correlation functions, entanglement entropy, But if we succeed in the first part, we will have achieved some important goal, which is to say that we could tame this world sheet, we could tame this string, exploit its integrability, and get to a final solution. If we can do it, then we can just say, well, all these other quantities, it will be very interesting to compute them, and we should, but probably, if we can solve one problem of taming this string vibrating, then all these other quantities will probably be related to the same process where the string now has a different topology. For example, if what we are considering is a string that is vibrating and so on. If I want to study 3-point functions, I want to study a string that is like this and then splits into two. So it's the same material, but now I tailor it not in a cylinder, but into some pair of pants. But it's the same string vibrating. So if I can tame this object and understand the quantum vibrations of this string, I can then put this string in a different format, like parachute, pants, cylinders, whatever. So first I have to make a proof of principle that at least for some topology we can nail this problem completely and sum over all string surfaces and compute the full string partition function, or in other words, sum all possible planar tooth diagrams. That's goal number one. Goal number two then be, what about then different topologies and how do we tame this surface when we start putting it in different topologies? So I would say that we right now have the full solution. I think the full solution in its best form appeared last year with the final set of equations that really describe the spectrum of strings at any coupling, which are a considerable improvement over something that we had done before, which was already the solution, but this is much better. It's called the so-called quantum spectral curve. I think that is the pinnacle of all this effort. It's really the very top, I think. And understanding these other quantities, which in a way is way more exciting in the sense that there is no recipe book, there's no book we can open in integrable models like there is for solving these time models that we can use. We really have to develop new tools. Is basically the main activity of many people right now trying to understand this very last point here. So we are now approaching with this blackboard really the boundary of what is known. So tomorrow I will elaborate a little bit more on the top part of this blackboard, telling you some things about all these points. Of course, with one lecture, I cannot really solve all of them, but I will try to tell you a little bit. It will be more like a story rather than a sharp derivation. I will tell you a little bit, what do we know about this? What is this mysterious dispersion relation? How do these bit equations look like? How does the dressing phase in ADS-CFT look like? You see, this is already a bunch of gamma functions. You probably want to see how does the ADS-CFT one look like? Just to see, just out of curiosity, what could replace that if we now have the ADS-CFT system? And I will tell you a little bit about the top, and then at the very end, just more informally, I can tell you a bit about more recent explorations and what kind of ideas people are doing, but this is very much ongoing stuff. I mean, most of it not even published that I can tell you a little bit about, but it's really not at the stage where we can yet present it in a sharp way. This is where we stand. Okay, very good, so let's continue tomorrow. I'm almost on time today.